Good evening. We are going to start on lecture number 3 of Power Electronics and EV Drives course. In the last class, we had looked at diodes, thyristors. In thyristor family, we had looked at SCRs, GTOs, and also IGCT. So I had just made a passing mention of IGCT. We really didn't get into any details of IGCT. We also looked at BJTs, power BJTs. And we said that because of their disadvantages, like they cannot be operated in parallel, the base drive requirement is very, very large, and the turning off actually takes a little longer if we try to use them in Darlington pair configuration. I'm not sure I mentioned this. So BJT actually, if we want to reduce the base drive requirement, then we can operate it as BJTs can be cascaded in Darlington pair configuration. So what we do in Darlington pair configuration is we will have one BJT connected like this, and its emitter will be connected to the second base of the second BJT, and here these two collector will be connected together. So this will be the base current, what we actually pump into transistor number 1. And let's say this is transistor number 2. And the emitter of this particular transistor is going to be grounded. And if at all we are looking at the load, what is connected will be at the collector of the collector terminal of the both the transistors connected together. So this is IC. So if I may call this as IC, very clearly this will be, let us say, IC1 and this is IC2. So we are going to have IC equal to IC1 plus IC2. And IE1 should be equal to IB2, because you can see this is IB1, which is also passing into B2, that is base of the second transistor. So it looks as though the base current what we are pushing here, this IB overall is equal to IB1. So we are connecting two transistors together. So we would have roughly the beta of the Darlington pair. That is the current amplification of the Darlington pair is going to be approximately the product of beta 1 and beta 2. That is, if I just take what is beta 1 for the first transistor, current amplification is IC1 divided by IB1. That will be beta 1. Similarly, IC2 divided by IB2, which happens to be emitter current of the first transistor. That is beta 2. So we are going to have this to be approximately, let us say if each of the beta current amplification is about 10, we said that when the transistor actually gets into saturation, the current amplification factor is going to decrease, because of which both of them put together, it will be almost as high as 100. So the current amplification factor increases quite a bit when we are trying to use two transistors connected together in cascaded manner as a Darlington pair configuration. But one problem with Darlington pair configuration is Although the base drive requirement decreases because of beta 1 and beta 2 being put together, or the product of the whole thing becomes the current amplification factor, the base drive requirement decreases. But because both transistors are now driven into saturation, to sweep out those charge carriers, to make them go into off condition, it takes even longer. So that becomes kind of a big problem for Darlington pair configuration, although it reduces the current requirement of the base drive quite a bit. Now, the next device that we wanted to see was MOSFET, Power MOSFET. Power MOSFET is a voltage controlled device. It is a voltage controlled device. So in a power MOSFET, generally you are going to have 3 terminals again. And this is the symbol of the power MOSFET. So I may call this as drain. And this is the source. And this is the gate. These are the 3 terminals of the power MOSFET. What we have shown here is an N-channel MOSFET. So in an N-channel MOSFET, what we are going to have is something like a P substrate. So this is a P substrate. P-type semiconductor substrate. In this, we are going to have some N material being doped here. And again, another N material being doped here. So I am going to have N plus. That is quite a lot of doping here. The same way this also is going to be N plus. Now, from here, the terminal that is connected, I may call this as drain. And from here, the terminal that is connected, that is source. Now, in between, we are going to have an insulator. So this insulator is invariably a SiO2 layer, silicon dioxide insulator. And from there, we are going to have a small metal connection, and this terminal that is taken out is gate. So this is going to be the gate terminal. Now, because there is an insulator here, if I apply a positive voltage with respect to source, then we are going to have negative charge induced or accumulated here, depending upon how much is the positive charge that I have, positive voltage I have applied in the gate terminal, there is going to be negative charge accumulated here. Whenever we are talking about N-type semiconductor, it is like having a lot of accumulation of negative electrons here. Basically, electrons are going to be accumulated here too. So we will have similarly electrons are accumulated here. Now, here also, because there is negative charge accumulation, if I apply a positive voltage here, there will be a thoroughfare or thorough movement, a thoroughfare opened up, a channel opened up for the movement of the charge carrier. So we are going to have, if I connect positive here and negative here, a power supply here, and if I apply a gate voltage with the positive polarity, then we are going to have negative charge accumulation here. And this is actually opening up the channel. Channel gets opened up. And because the channel gets opened up, we will have essentially a flow of current from drain through the channel into the source. So we are going to have a straightforward current flow provided the channel opens up. So power MOSFET essentially gets into conduction right away if I apply a positive voltage in the gate with respect to source. So it is very quickly, it can be turned on. And similarly, very quickly it turns off as well. So turning on and turning off both can happen very quickly because it is just the application of voltage and how long it takes this gate to the channel, that capacitance, how much is the capacitance value, how long it takes for the charge accumulation or charging to take place. So this is essentially working based on capacitive effect. So you don't really need a large current to be, pass through the gate terminal at all. So turning on is basically very simple and it is a voltage control device. So you don't require really a high power gate driver circuit for the power MOSFET. And invariably what we see normally in the market are N-channel MOSFET because the electron mobility is much better. As a charge carrier, generally electron actually moves very fast, and that is the reason why generally N-channel MOSFETs are the ones that are present in a power semiconductor device area. Only one problem normally we see, especially in power MOSFET, if we are talking about large voltage rating, is between the drain and source. If it has to withstand a very large voltage before being turned on, the distance has to be larger. The channel, that means, becomes larger even during conduction. The length of the channel, this is the length of the channel that becomes really large during conduction. If we want to increase the distance between drain and source because it has to withstand a large voltage, under such a condition, the resistance between drain and source during on condition, this is going to be larger for large voltage rating. So the turn on losses, so on time losses are going to be higher. These are higher for a MOSFET as compared to a BJT. BJT, we said VCE is generally only going to be 0.7 volts once it gets into saturation, but that will not be the case in the case of MOSFET. You can have the resistance, drain to source resistance during on condition can be larger. So on-time losses could be larger in a MOSFET. So only problem with the MOSFET is that we are going to have a higher loss during on state. And also, if we have to make the MOSFET for larger rating, this channel length has to be increased further and further, and the device becomes too unwieldy. So that is the reason why the ratings of MOSFET are limited. And when we look at this kind of MOSFET, one major problem normally what we see is that if the losses are higher, you will require a larger heat sink also. So let me show some of the devices that are available in the market. I just wanted to show you. This is typically a fast recovery diode. And you can see this is one of the fast recovery diode that is available in the market. So you have only two terminals. One will be cathode. So this white color thing, ring, will be cathode and the other one will be anode. So this is typically a diode. So you can see one more diode here also. This is also a diode that we are looking at. So I would show this is typically a thyristor. So in this thyristor, you can see that this is the gate, and on one side it is anode, and the other side will be cathode. So you will have 3-terminal device. This is a very, very large capacity thyristor. And you can see these are the heat sinks typically. So this is a heat sink where you can see a hole here, and your device will be actually bolted along with this heat sink, and the heat sink will be generally having a larger surface area because of the fins around. You can see even in this case there are fins. So these fins will increase the surface area so that it can dissipate the heat, one thing. And second thing is that they will be painted in black because it can radiate the heat much better. That's one more thing. And when it is bolted together like this, if we look at the thyristor here, you can see from this particular hole, along with this, it will be bolted. So this terminal, whatever is available, that will be, or if we are bolting from this side, whatever is this terminal, if it is cathode, it is essentially connected directly to the metal body of the heat sink. So this will also be carrying the same current. It will be actually short circuited with the other terminal of this SCR. And by the way, when we read the data sheet, this is typically a data sheet of one of the thyristors. So this is actually a ST700CL series thyristor SCR. You can see that what is the reverse maximum voltage and forward blocking voltage it can withstand. So there are the series, we have said ST700CL series. It can be CLT40, CLT80, and so on. Accordingly, it can withstand either 1200 volts or 1600 volts or 2000 volts and so on. So what is the kind of gate current requirement and so on? All these things are given. So if you actually look at it, this is the maximum current what it carries on an average basis, not maximum current. On an average basis, it is capable of carrying 910 ampere, and the temperature it can withstand is about 55 degrees centigrade. And what is the kind of RMS current it can carry? That is about 1857 amperes under normal 25 degree centigrade operation. So you can see many of the things what it is talking about, what is the frequency at which it can operate, and under such a condition, what could be the turn off time. So for turning off, it takes about 150 microsecond, it is shown. So you would be able to read the data sheet by looking at what all are the voltage ratings and current ratings given, and correspondingly, you would be choosing a particular thyristor for your application. So I was thinking I should just show you at least the kind of data sheet that is available so that you know how to read a data sheet. That is important. So you should read the data sheet before you select a particular device for your circuit, because you should be able to, first of all, design your circuit. You should be able to see the simulation by looking at what is the maximum current, each of the points at each of the nodes, what is the kind of current, how much is the device current that is being carried in the circuit, and accordingly, you will choose your devices when you are actually making the circuit in the hardware, finally. So to conclude our point or discussion about MOSFET, most of the power MOSFETs are N-channel MOSFET, and generally their on-time resistance is much higher than BJT. That is the reason why the losses could be higher. So heat sink requirement might increase, and it will have basically voltage based turn on. So you don't require a high gate current for turning on the MOSFET. and it is very quick in terms of turning on and turning off. And the protection again for MOSFET becomes a little difficult because fuses are slow acting compared to MOSFET. So you need to really, monitor the voltage and current through the MOSFET to protect it. Continuously, you have to monitor that. And the moment maybe the current increases beyond whatever it can withstand, immediately the gate pulse need to be removed. Only then the MOSFET can be protected. So the next device that we are going to look at is IGBT. This is insulated gate bipolar transistor. So insulated gate bipolar transistor is actually a hybrid between BJT and MOSFET. So this is a hybrid between BJT and MOSFET. So it combines the advantages of both BJT and MOSFET. So if you actually look at BJT, BJT can turn on, it requires a high gate current or high base current. Whereas its on-state drop is small. But MOSFET actually requires very low gate current. And it operates at high frequency, but on-state drop is high. So if we want to combine these two, we should be able to turn on the device at very low gate current, but simultaneously, we should also see that during on time, the drop is not very high. And IGBT, basically, the symbol is something like this. So this is the emitter, and this is the collector, and the gate is insulated. So this is the gate. So that is the reason why we are showing one more line, and between this base and this gate, there is an insulation. So this actually consists of, the IGBT is made up of, on the front end or at the gate end, there is a MOSFET amplifier, and the MOSFET's output is given to a transistor. And it is a PNP kind of transistor. So we are going to have a transistor like this. So this is basically the total structure of the IGBT. So because there is a MOSFET amplifier sitting in the gate side, a small voltage. So here if a small positive voltage will turn on this IGBT. There is no problem at all. It will automatically turn on the IGBT. Whereas the MOSFET, once it turns on, its output current is going to trigger this PNP transistor, and that is actually going to drive this transistor into saturation. So the on-state resistance, what is visualized actually at the load side, that is going to be really, really small. This transistor is driven into saturation, because of which we are going to have the on-state drop to be very small. So this is essentially looking at, if we say MOSFET is having almost something like a few nanoseconds of turn on and turn off time. And if we talk about BJT having a drop of only about 0.7 volts or 0.6 volts, Both are combined together in the case of IGBT. So IGBTs can easily operate at, let us say, something like 20 to 40 or 50 kilohertz. Very easily they can operate. In fact, the frequencies are being pushed further and further up. And they are also available almost at 2 or 2.5 kiloampere with about 2 or 3 kilovolts single-handed. So they'll be able to handle almost megawatt of power level. And even under that condition, the drop is not much. The losses that take place in IGBT are not much. So if I try to overall write about all the devices and try to draw a graph indicating what is the power level each of these devices can handle versus what is the frequency each of these devices can handle. So let me first of all write this is probably something like 10 hertz. And let us say this is 100 hertz. This is 1 kilohertz. This is 10 kilohertz. So these are all logarithmic scale. And this is also 100 kilohertz and so on. So this is 1 megahertz. Whereas power level, I'm going to say this is 1 kilowatt. This is about 10 kilowatt. This is 100 kilowatt. This is 1 megawatt. And this is about 10 megawatt. So this is the graph that I'm showing. So if you look at SCRs, SCRs are capable of operating only around 100 hertz or 50 hertz. So SCR can handle very easily a few tens of megawatts and only until about 50 hertz or 100 hertz. Whereas GTO can handle maybe until 10 megawatt, but they can easily go until, let us say, 1 kilohertz. So GTO I should show somewhere here. Whereas if I talk about some tens of kilohertz, and if I am talking about a few megawatts of power level, IGCTs can handle that much. Whereas if I'm talking about 20 kilohertz or 40 kilohertz and about 1 megawatt of power level, it will be about the range of IGBTs. And if I'm talking about 1 megahertz, 100 kilohertz to 1 megahertz, but about 10 kilowatts of power level, that is where MOSFETs are. So BJT might lie somewhere here. So this is kind of a graphical representation of what are the different power levels each of the devices can handle and how much of frequency level each of them can handle based on their turn on time and turn off time. So let me show the IGBT. So these are some of the IGBTs that are available in the market from Infineon Technologies. So you can see again, it's a 3-terminal device. One will be emitter, one will be collector, and the other one will be gate. And you can see also that there is a hole here which can be fixed into a small heat sink like this. And the heat sink has fins here which will actually make sure that the heat is radiated or flushed out very quickly. So the larger the losses, the bigger will be the heat sink. The size occupied will become larger by the circuit, and also the weight, because the heat sink is generally made up of metal. mostly iron or something like that. So that will also occupy a large amount of space. So that is the problem with the the largest size of the heat sink. So power MOSFET, you can see again, this is one of the power MOSFETs. This is from International Rectifier. There are various companies that produce these power MOSFETs and IGBTs and so on. So some of the companies normally you can look at the website to familiarize with some of these device producing companies. Semicron is one, then Mitsubishi Electric is another. Infineon Technologies is one more. And International Rectifiers. These are some of the companies which produce power devices. Even BHEL, for that matter, produces SCRs which can be used in normal 50 hertz rectifiers and so on. So we have seen different kinds of devices that are being used in power electronic circuit. So we will be starting with now AC to DC converters. We may also call them as rectifiers, but converters is a generalized terminology that is used for all the power converters, power electronic converters. But if we generically say converters, we assume that it might indicate AC to DC converter. So as the name indicates, from an AC supply, or the rectifier will convert, the rectifier converts bidirectional or alternating current into unidirectional or DC current. Typical applications when we talk about AC-DC converter is, the major thing is battery charging. So you see that generally, whether it is laptop charger, whether it is a mobile charger, or whether it is an EV battery charger, all of them require AC to DC conversion. Even inside your TV or any other electronic appliance like a monitor or even in an SMPS, which is inside a PC, all these things require generally AC to DC converter. And your DC motors, some of the DC motors that are used in industry, those, if you want to control the speed, then again AC to DC converters are used. So we'll first of all start with one of the simplest AC to DC converters. So we'll first of all say single phase diode rectifier. And I'm going to start with only one single diode. So that means we are having a single diode connected, and let us say a resistance is connected here. So if I may call this as Vs, and I may call the voltage across this as V naught, and let's say this is resistance and this is the diode, and the current that is flowing here is I. Okay. So we are looking at This diode will conduct only when this is positive with respect to, the anode is positive with respect to cathode. And if I'm talking about this as a sinusoidal voltage, Vs will be equal to some Vm sine omega t. So this actually I can plot as this is how my sinusoidal voltage is, and this is omega t. So this is 0, this is pi, and this is 2 pi. And if I say that 50 hertz is the frequency of this supply voltage, so this is going to be the frequency. So time period is 1 divided by 50, which is actually 20 milliseconds, which indicates that this is going to be 10 millisecond. And again, this is going to be another 10 millisecond. So the diode will conduct only when the anode voltage is positive with respect to cathode. So only during this portion, that is the initial 10 millisecond portion, you can see that the voltage is positive. What I'm applying from here is positive. So the anode is going to be positive. So the diode will conduct only during this portion. The other portion, the diode is not going to conduct. So the current will flow in this circuit only when the diode is actually forward biased. Otherwise, it's not going to be, the current will not be able to flow. So this is the current that is flowing through the circuit. And Vs divided by R is going to be equal to I when the diode conducts. So V0 will be available only during this portion. So this is going to be V0. Whereas during the reverse half cycle, the diode will not conduct, it will be off. So we will have essentially V0 to be 0 during this portion, and V0 is going to be equal to Vs during this portion. So when the diode conducts means this is from 0 to pi is going to conduct. And I is going to be equal to 0 when omega t is from pi to 2 pi. So during the negative half cycle, the current is going to be 0. It is not going to conduct at all. So under this condition, what happens now is that we would see that the the voltage, if it is like this, the output voltage, if it is like this, then the current would be this voltage divided by resistance. So that will also be sinusoidal. So this is V0 and this is I0, which is actually flowing through the resistance itself. Now we should be able to derive what is the average voltage across the load. So that is going to be integral of 0 to pi, because from 0 until pi, it is going to be Vm sine omega t d omega t. But it has to be averaged over the entire cycle, because it's conducting only for half a cycle. The next half cycle, it is not conducting. So it has to be averaged over 2 pi. That is the average value of voltage across the load. So this will be Vm divided by 2 pi. And for sine, the integral is minus cosine. So I should be able to write cos omega t. And let me change the limits as pi at the bottom and 0 at the top. So this will be Vm divided by 2 pi multiplied by cos of 0 minus cos of pi, which actually would give me 1 plus 1, 2. So this will be Vm divided by pi. This will be the average voltage across the load. So average current through the load, that will be Vm divided by pi R. This will be the average current through the resistance. Okay. So this is essentially the basic principle of operation of the half wave rectifier. And in the half wave rectifier, although we are giving AC here, what we get here is only unidirectional voltage. The current is going to flow in this direction, and the voltage will be always positive here with respect to the other end of the resistance. So if we connect an RL load, so we call the single diode connected to the AC supply as a half wave rectifier because only half of the sinusoidal wave is going to the load. Rest of the half is not passed on to the load, so we call this as a half wave rectifier. So in half wave rectifier, we have only one diode, and instead of connecting a resistance, now I want to connect a resistance and inductance, both. So if I connect the resistance and inductance to a half wave diode rectifier, what happens to the output voltage? So when we write the equation, if I call this as Vs, and Vs is going to be Vm, generally the voltage what we write as instantaneous voltage, it is probably easier to write it in small lowercase letter. So let me write this also as small Vs, which is equal to Vm sine omega t. That is going to be equal to, if I say the current that is flowing is I, so I should write Ri plus L di by dt. What I'm writing is the Kirchhoff's voltage law equation. And this is true when the diode is forward biased. This equation will be valid when the diode is forward biased, whereas current will be equal to 0 if the diode is reverse biased. Forward biasing is when I have plus here and minus here. That is, anode is more positive with respect to cathode. At that point, this is going to be the equation which is governing the operation of the circuit. So I should be able to say Vm sine omega t minus Ri is equal to L di by dt. So this tells me that when Vm sine omega t equal to Ri, when Vm sine omega t equal to Ri, I'm going to have di by dt is equal to 0, or I will reach its maximum value. Okay. So if I try to draw the waveform, I should say this is my input voltage. with respect to omega t. So this is going to be Vs. And initially, when Vm sin omega t is greater than Ri, because I is 0, when I start, the current is going to be 0. The voltage is also 0. But it is starting from 0 and slowly increasing. The current is increasing depending upon what are the relative values of R and L. So the current is slowly increasing as long as Vm sin omega t is greater than Ri. Only then di by dt is going to be positive. So the current is going to increase. So let us say the current reaches somewhere its peak value at some point. Now at this point, Vm sin omega t and Ri will be equal to each other. One thing you have to realize is if I say this red color thing is current, I times R is just a scalar multiplication. So I will have I times R somewhat like this. So if I times R is this green color waveform, and Vm sin omega t is this black color waveform, you can see that at this point, Vm sin omega t and IR are equal to each other. So at that point, the current would have reached the peak. After that, the current should start decreasing. So the current will start decreasing and probably it will reach 0 because after this point, if I try to look at what is IR, IR is somewhat like this. IR is going to be somewhat like this. Because it's a scalar multiplication of the current, this is what is IR. So until this point, Vm sin omega t was greater than IR. But after this point, if I may call this point as some beta 1, and this is 0, and this is pi, and let me call this as beta, this point as beta. So from 0 to beta 1, Vm sin omega t is greater than Ri. So di by dt is positive. Current is increasing. Current increases until then. Now, from beta 1 to pi, Vm sin omega t is less than Ri, although Vm sin omega t is still positive. Vm sin omega t is still positive. So I'm going to have Vm sin omega t minus Ri equal to, it's a negative value, and L di by dt, because it is negative, this di by dt itself is going to be individually negative. Inductance is a positive quantity. It cannot be negative. So L di by dt, out of this, di by dt is going to be negative. So this is negative. And Vm sin omega t is positive. So if I take it to the other side, Vm sin omega t minus L di by dt equal to Ri. But this minus L di by dt will be now positive because L di by dt is negative, minus L di by dt is positive. So these two join hands to take care of the resistance drop. So from beta 1 to pi, from 0 to beta 1, Vm sin omega t was taking care of whatever is the resistance drop and inductance storing the energy. Di by dt is positive, means inductance is storing the energy. Now inductance has started returning the energy. So that is joining hands with the positive voltage to take care of our IR drop. Now from pi to beta. So if I try to look at from pi to beta, you can see that the voltage is negative. The voltage has started becoming negative. But still the current is continuing because the inductance is still returning the stored energy. So Vm sine omega t has become negative. It has become negative. And Vm sine omega t minus Ri, because this is also negative and this is also negative. Now, both of this is a drain on the overall energy that is there either in the source or in the inductance. And Vm sin omega t, because it is negative, even it will be a drain on whatever is the inductance stored as energy. That is going to be equal to L di by dt. So the inductance stored energy is going to forward bias the diode, and hence the diode conducts, and the driving force now is inductance stored energy, and it is going to take care of both the voltage, which is already negative, voltage source, which is negative, and the resistance drop put together. So if you look at the voltage, what comes out across the load, that is essentially present until the current is non-zero value. So if I try to draw what is the voltage waveform that I'm going to have, it will start from 0 and it will end until beta. So it is going to be somewhat like this. This is the kind of voltage that I'm going to get across the load. So it starts with 0 and it goes on until beta. If it is larger and larger inductance, this conduction can increase further and further to make sure that the current continues for longer, the diode is forward biased for longer against even a negative voltage, which is coming up from the source. So in general, if I have a larger inductance, the conduction increases further and further. We'll try to do a little bit of simulation in the next class and show what happens with respect to the effect of L to R ratio, that is inductance to resistance ratio, how that influences the overall conduction of the diode in a half-wave rectifier circuit feeding an RL load. Okay.